All right. Hey, everybody. So today we will be talking about clustering, which I would say is probably the most common unsupervised learning thing that people will do. I guess it's clustering and PCA, which are the two unsupervised topics we're talking about. But clustering is very, very commonly used, and you can use clustering for many different things. If not for the act of clustering, clustering can also be a really helpful EDA tool. And I'll talk about that more later on. First to start, before I get into the details of clustering, again, I'm going to reiterate the differences between supervised and unsupervised learning. So as mentioned yesterday in different words, in supervised learning, the system's trying to learn from previous examples that are given. In unsupervised learning, the system is attempting to find patterns directly from the examples given. If the data set is labeled, basically if you're trying to predict something, it is supervised. And if it is unlabeled, it is usually an unsupervised problem. So supervised learning here, you see we're trying to classify X's and O's. And here we're forming groups based on the distribution of our features themselves. So clustering specifically, for clustering, the data is basically trying to be divided into several groups. In plain words, the aim is to segregate groups with similar traits and assign them into clusters. So if you ever had a data set and you wanted to figure out, okay, what are some of the overarching main characters in this data set, you can do some clustering and then look into, all right, let's take a look at all these green folks. Seems like all these green folks have like values mostly above 2 for this dimension. Maybe that means something in your data set. You'll do the same thing for your blue group and your red group, and you'll basically try to make some sort of conclusion based on the groupings that are formed, and that will help with either your EDA. Maybe it's a task that you want to do. For example, market segmentation is a clustering problem. If you have like a bunch of users and maybe their, I don't know, shopping activity, you could segment your users into several groups so that you could do like targeted ads as an example. So that is also another application of clustering. To go an overview of clustering types, today we are actually going to just focus on hard clustering, but broadly it can be divided into two subgroups. Hard clustering, which is when every data object or point either belongs to a cluster completely or not. For example, if you want to cluster NYC locations, every location is either in one borough or another. It's either in Brooklyn or in Queens. It cannot be half-half, for example. Now in soft clustering, you could have half-half. In soft clustering, a data point can belong to more than one cluster with some probability or likelihood value. For example, as I was mentioning before, some locations could be border points belonging to 2 or more boroughs. So pretty much the differences between these two clustering types are the kinds of outputs that you get. For hard clustering, your output is literally what cluster it belongs to. And for soft clustering, it could be an array of probability values for which cluster, or the probabilities related to the data point belonging to each cluster. Both these clustering algorithms, actually one of the clustering algorithms we're going to talk about does have a soft clustering output as well. I'll talk about that later. There are two main kinds of hard clustering algorithms, and we're going to actually talk about one model from each of these. First, there's centroid-based clustering, where your clusters are represented by a central vector or a centroid. So you can kind of characterize a cluster by its middlemost values, and how that is computed we'll talk about later. And the centroid doesn't have to be a member of the data set. So it doesn't have to be, okay, data point number 57 is the center of the cluster. It could be like an average, or it usually is an average of all the data points assigned to that cluster. Centroid-based clustering is iterative, in which the notion of similarity is derived by how close a data point is to the centroid of the cluster. I have a really cool GIF, the one that I actually opened up. I'll show you all how that works under the hood. K-means clustering is the algorithm that we're going to be talking about. It is centroid-based, and you'll see this in a little bit more detail. The other kind of clustering algorithm we're going to talk about is connectivity-based clustering. The idea behind this is that data points that are closer in the data space are more related than data points further away. Makes sense, right? If you have two movies and the only difference in the movies, let's say, is their maybe you have the same movie but dubbed in different languages. Those two movies are going to be extremely similar because all of their features are the same except for one. So that's an example to talk about closer in the data space being more similar versus points that are further away. We also have some visualizations to showcase how this works, but the clusters are formed by connecting data points according to their distance. At different distances, different clusters will form and can be represented using a dendrogram, which is why they're called hierarchical clustering. We'll actually have a couple examples of dendrograms, and it shows how this hierarchical nature of this kind of clustering algorithm, how that works. So these methods don't produce a unique partitioning of the data set, rather a hierarchy from which the user needs to choose appropriate clusters by choosing the level where they want to cluster. We'll get into that later as well. Also, not very robust towards outliers, which may show up as additional clusters or cause other clusters to merge. So we're already starting to see some of the slight differences in these two. One commonly used phrase, I actually like to think of centroid-based clustering, which is K-means that we're going to talk about, as a top-down clustering, where connectivity-based clustering, and the algorithm that we're going to use is called HAC, which stands for hierarchical agglomerative clustering. That's more of a bottom-up approach, and we'll sort of see how those two approaches are not completely opposites, but how they're approaching the data set from different angles. All right, so to do this, I'm going to use a very, very simple data set. So we take a look at data. It's only going to be 2 columns of data, and we're going to cluster this data. If I actually quickly plot the scatter plot of this, I think that'll be helpful to see. plt.scatter, and we want to see, oops, what's going on with my screen here. plt.scatter, data v1 and data v2. So data v1, data v2. Cool. So this is what the data set looks like. Just looking at this from, just eyeballing this, it looks like there are going to be 3 groups, but we'll take a look to see how certain points like in the fringes of these groups will be clustered. All right. So K-means clustering is the first one we're going to talk about. Now, this is the centroid-based clustering method. Before I talk through all these details, I do want to show you all this GIF of how clustering works. I'm going to refresh it. I'm going to give you a quick intro and then refresh it. So how this works is you first select the number of data points of the number of clusters that you want. So one thing about clustering, similar to PCA, is you start by telling the model how many groups you want to end up with. So in this case, with this data set, I say I want to end up with 4 clusters. And what's being done is you're going to select 4 random data points to be your starting centroids. So as you can see over here, oh no, let's get this back. Wonder why it changes. All right. Okay. So over here, you see that it started with these 4 data points on the left. And then what it does is it goes to look at all of the other data points in the data set and assigns every data point to the closest centroid. Then the next iteration, it recenters these green dots to be the center of whatever data points are connected to it. And after a while, when the centroids don't shift anymore, those are your final clusters. Any questions about how this is working just based on this first, before we talk about any math, any metrics so far? Okay. All right, so how this works is, as I mentioned before, it takes the K number of centroids or data points in its account initially. So after choosing the centroids, and for example, if I start with C1 and C2, all the data points are assigned to any of the clusters based on the distance. So let's say if I'm starting over here and over here, let me actually annotate real quick. Let's ignore what's there first. But let's say one centroid is here, one centroid is here. And let's say I'm only doing 2 centroids. The very first iteration, I'm going to basically assign every data point to its closest centroid. So all the data points on this side will be assigned over here. All the data points on that side will probably be assigned over there. And then after those assignments are done, it gets recentered. Let me clear this and scroll back up the explanation. Where am I? Oh, distance metrics. We're going to talk about that in a little bit, of different ways you can measure distances. But the algorithm will basically continue to update cluster centroids until they can't be updated anymore. And then the new centroids, again, are determined by the average values. So as you can see, usually the green dots end up being in the middle of all the data points associated with that cluster. And yeah, no longer updates the centroids when there is no change in the current cluster formation. So here are just some examples using different initial centroids. This early one that we had, if you remember, started the centroids on the left over here. If we take a look at a different one, as you can see that these results are different. Let's take a look at this one over here. If I start my centroids on the right, you can see that we have this one outlier over here. And this is actually something that happens pretty regularly when it comes to clustering. Let's wait for this to move for a little bit. You see how the centroids shift to be in the middle of everything that it's connected to. Readjust, you end up with this outlier point over here that's its own cluster. And that's pretty normal, especially when you have a very noisy, outlier prone data set. So this is just an example of with different starting points, you can end up with different clusters. Now within scikit-learn, let me actually pull up the scikit-learn documentation while we're at it. This is called k-means clustering. The initialization of your cluster centers, by default, it uses its own smart way of choosing initial clusters. So I typically don't really mess with this unless I know roughly where I want my centroids to be. But typically you don't have that information to start. I've actually never changed the initialization. So initial cluster centers are selected by the algorithm in this case. Okay. So this just goes to show that starting with different centroids, you can end up with different results. This is starting on the left. You can see starting on the right, it looks like this. Starting in the top and bottom, I think look fairly similar as well. But just the difference between left and right, you end up with different clustering results. All right, and if we do this, the way that we use our clustering algorithm is all you do is instantiate your k-means, tell it how many clusters you want, fit it to your data, and then you can do your dot predict. So when you fit it to your data, I'm also going to do a quick dot describe to see the distribution of my two features. I know this is not really it's not contextual or anything, but we have V1 and V2 for now. Within your k-means fitted object, you can get your cluster centers. So I can see from here, my 3 cluster centers are at this this center, and this center. So you can start to see the differences already. Maybe off of the V2 axis, you can see that the min and max are like 38 to 87, negative 38 to 87. One of the centers are at negative 10 on the lower end. One of them is sort of in the middle at 10, another one is at 59. You sort of see the same thing over here. Maybe if these are maybe something like height and weight, you can start to make some conclusions about the nature of each cluster. But from here, we can do a dot predict on our data to get our cluster labels. So over here, I have my k-means dot predict. I'm just adding that as a column of my data set, and I can plot that as well. Oops. Cool. So these are my clustering results, kind of intuitive. You saw that before I even color coded it, you could sort of see where the groupings will be. And you can sort of see that also here, the fringe data points have been clustered as such. Cool. Questions about this algorithm as a whole before we talk about evaluating clustering?
A quick question, would any like outliers affect clustering, or does it take in outliers? Or
yeah, so outliers do affect your clustering results. Sometimes if in this example, you saw that this outlier over here, if that happened to be selected as an initial centroid, it is very likely that it ends up being like a 1-point cluster by itself. So even though I asked for 4 clusters, 1 cluster just has 1 data point. And that's actually very commonly what happens if you have very sparse data, or if you have, outliers like this. Typically though, within k-means, because of the way that it does its random initialization, not random, but the way that it does its smart initialization, smart way, the way that it does that doesn't typically happen. But if you, let's say, take this data set and say that, okay, I want to have 20 different clusters. It's hard to say, but maybe there's a chance that this point out here might be like a 1-point cluster on its own, which we'll get it. I'm next going to talk about what's the best, how do you decide on the best number of clusters? But yeah, outliers do have an effect on clustering results. Also, because k-means is, especially the initialization is fairly, there's an element of randomness to it. Every time you rerun k-means, you're going to get different clusters. Or maybe if your clustering results don't differ too much, the labeling might change. So for example, I think if I rerun, where's my dot fit? If I rerun my dot fit, and you can see that it started out as 0 here and then 1 at the bottom. If I rerun this, we end up with 1 and then 0. And then the colors also will flip. So it is possible that they selected similar centroids, but in a different order. So be careful that when you do your clustering, you might want to do a random seed.
All right. Thank you.
You're welcome. Anything else? All right. So let's talk about finding the best number of clusters. This data set, it was super obvious how we were what our clustering results would look like, because there are kind of 3 obvious blobs of data there. Typically in most data sets, that is not the case. Now, finding the best K, and best K really is subjective, I will say. Sometimes you are kind of constrained by your business problem. So as an example, let's just say you work for a marketing firm and they're asking you to do some customer segmentation. And they're like, okay, we have enough budget to do 5 different campaigns for 5 different groups of people. Then you have no choice, but you have to cluster it to 5. In that case, maybe you don't have, you just don't have the freedom to try different numbers of clusters. Maybe you want to try 4 so you can save them one group of, I don't know how marketing works, but that's a possibility. However, if the goal is not to get a certain number of clusters, but your goal is to just cluster and create new groups of your data, you can play around with the number of clusters that you use. And there are a couple metrics that you can use to do that. So one of them is the WSS elbow method. So WSS stands for within cluster sum of squares. So the basic idea behind k-means clustering is to define clusters such that the total intra-cluster variation is minimized. So basically, if I were to compare the distances between each data point and its center, you want that to be as minimal as possible. So literally, if let's just say that this over here is the middle of this cluster, I am measuring the distances between every data point and this center point. And we want to make that as relatively low as possible. You're going to do the same thing over here. We're going to add these 3 sums together. If you have very tight clusters, that means you have lower WSS, which is usually what you want because it's well-defined groups. So total WSS measures the compactness of the clustering, and we want it to be as small as possible, right? We want compact groups that are very clear in their, I guess, boundaries. So the elbow method looks at total WSS as a function of the number of clusters, and you should choose the number of clusters so that adding another cluster doesn't improve the total WSS by much. So if you think about that statement, I know that's a lot of words in a sentence, but let's just say that, okay, if I had 1 cluster, if this was 1 gigantic cluster, the distance is going to be the sum of distances from here to the center, right? And these distances are obviously going to be longer. So naturally, your WSS is going to get smaller the more clusters you have, right? If you compare this distance with 1 cluster and this distance with 3 clusters, there's already a huge dip in your WSS. If you were to do 6 clusters, that would be even smaller. Let's just imagine 6 clusters kind of divides each cluster by half. With 6 clusters, your distance will naturally decrease. So there is going to be a natural decrease in WSS the more clusters you have, but you kind of want to look at the marginal decrease in WSS from as you increase the number of clusters. As an example, I ran WSS for 2 to 9 clusters. And you can actually get your WSS score from k-means.inertia. Inertia is basically the WSS for k-means. And the curve looks like this. You can see that with 2 clusters, this was the WSS. And then at 3, it really dramatically goes down. Then 3 onwards, the decrease is a lot, the marginal decrease is not as much as it was from 2 to 3. So this is why this is called an elbow curve, because you're looking for the elbow to determine what a good number of clusters is. Because the elbow, or the biggest change in the marginal improvement, is at 3. 3 is the best number of clusters. Questions about this? All right. It's not always going to be this obvious. I mean, for this data set, I mean, it is pretty clear that 3 clusters is a good number of clusters, but that's not always the case. You might sometimes see something that looks like, let's say something that looks like this. And then you kind of have like 2 elbows to choose from. And at that point, it really depends on your business problem, what makes more sense. Or maybe you don't want to have as many clusters, you would choose a smaller one, really up to you. There's a lot of flexibility that you can have, again, depending on the business case. But yeah, usually it's not this clear. There's also a chance that it might go back up at some number, but you're overall looking for where, yeah, it's kind of a balance of business context and also where WSS scores have this big change in the gradient. So it would either be something like here, probably, maybe here. All right, so we're looking for the elbow of the graph where marginal decrease in WSS is subsequently reduced. And based on this graph, best K is 3, as expected. Another metric that's commonly used for figuring out the best number of clusters. And again, these best number of clusters, these metrics, if you put into perspective, these metrics are purely mathematical determinations of best number of clusters. Sometimes if it tells you your best number of clusters is 3, but in your business context, it makes sense to have 5, I would actually always go with what makes more sense in context over what math is telling you. All right, so another one is silhouette coefficient. So average silhouette basically measures the quality of clusters, how well each object lies within its cluster by estimating average distance between clusters. So what the silhouette value is measuring how similar one data point is to its own cluster compared to other clusters. So silhouette score ranges from -1 to +1, where a high value indicates that it is well matched to its own cluster and poorly matched to neighboring clusters. So basically, if someone is, or if a data point is sort of at the fringe of a data set, it would have a low silhouette score. And if a data point is in the middle of a data set, it would have a high silhouette score. So if we take a look at this data point over here would have a high silhouette score, but one that's over here, because it has similarity to this cluster as to this cluster, might have a lower silhouette score. So you're kind of looking at average silhouette score over an entire cluster. So over here, if most objects have a high value, then clustering configuration is appropriate. If most points have a lower negative value, then clustering configuration might have too many or too few clusters. Silhouette can be calculated with any distance metric as well, such as Euclidean or Manhattan distance. So if you take a look at this, I'm running it from 2 to 19. Over here, I'm fitting my k-means and I'm grabbing my silhouette score from here. And over here, you can see that it, again, peaks at 3 clusters. And after which it's really dips down because that relative to other clusters, it's much lower. So for this data set, it makes sense because if I were to split each cluster into 2, so let's just say I have this dividing line over here and I look at this data point here, it's the relative distance between this cluster and let's say this cluster is going to be less of a difference, if that makes sense. So basically, you typically see some sort of arch pattern when you're looking at silhouette scores. All right, any questions about these 2 metrics? And these 2 metrics will also apply to HAC, which we're going to talk about next.
Would you recommend doing one over the other or using both to like really hammer the best K.
If you have the freedom to pick your best K, I would usually do both, just to get, I don't know, wisdom of the crowd. Yeah.
Got
Mhm.
Gotcha.
Yeah.
Okay.
And it's not uncommon to actually see different results from either metric, and then it's really up to you to decide which one makes more sense in your business problem. All right, so struggles of k-means. There's this really great article over here, but to summarize this article into 2 data points, into 2 broad summary points, that article demonstrates that there is an ideal kind of k-means data set and also shows some scenarios where k-means struggle. So highly recommend reading this. It's not a very dense, okay, it looks kind of dense, but it's not a very in-depth article, but it's really cool to talk about. It's a really cool article that demonstrates why k-means clustering has its limitations. Okay. Oh, one more thing to mention, because k-means is comparing, it's comparing the distribution of your features in feature space. I don't think I mentioned, I'm not sure if I mentioned it anywhere else, I kind of forget, but it's always important to scale your data before throwing it into a k-means clustering algorithm or any clustering algorithm that takes distance into consideration, for the exact same reason why you want to always scale your data before using a k-nearest neighbors model. All right, sorry, I've been scrolling up and down a bunch. Okay, so the next clustering algorithm we're going to talk about is the bottom up one, and this is HAC. The documentation is very, very similar. You're also going to tell it how many clusters you want. I have an implementation example later, but for this, we're going to talk about one hyperparameter, and that is linkages. I mean, we'll talk about linkages in a bit. So how does hierarchical clustering work? It sets out to group most similar observations together from a bottom-up level. So imagine if I have 100 data points. What it does first is it finds the 2 that are most similar to each other, joins those 2, and you just do that same process over and over again. I have a graphic that showcases that I'll show you all in a little bit. So initially, every observation is going to be its own cluster. Then most similar pairs of observations form a cluster together, and the next most similar groups fuse together, and we continue this pattern until you have one big cluster. What we end up then is a tree-like diagram called a dendrogram, which allows us to view clusters obtained for each possible number of clusters from 1 to n. Then we use our discretion to decide where to cut off the dendrogram, determining the number of clusters. So quick comparison between the 2. The goal of k-means is to assign individual observations to pre-specified number of clusters according to distance between centroid and observation. At the very beginning of k-means, you're picking your 4 center points and then assigning data points to those centers, and then you're shifting your centers iteratively. One disadvantage of k-means is that you specify the number of clusters beforehand, and theoretically, we don't have to do this with HAC. You'll see here that we still do tell it how many clusters, but it's actually computing the entire dendrogram up till that number. And I think I'll explain what that means in a little bit. So some quick pros and cons. Advantages: it is pretty easy to implement. It's quite intuitive because it's based on similarity between individual data points. And it's a little bit more informative than k-means. This is kind of subjective because it takes individual relationships into consideration. And it also gives us the dendrogram to look at. Similar to how in a decision tree, we can literally look at how the tree or how the feature space is being split up. With HAC and the dendrogram, we can actually see, all right, which points are forming clusters first. Some disadvantages: it is very, very sensitive to outliers. And you also cannot undo a prior merge, which might lead to later problems. And I'll show you all what that merge is all about. This is a bunch of code that is not relevant to us right now, but this allows us to make this graphic that I want to show you all. So when you initialize HAC, as I mentioned at the start, each data point starts as its own individual cluster. Then with every iteration, you see this merging start to occur. So at step 1, let me zoom in a little bit. At step 1, these 2 data points are most similar to each other. So these 2 data points are going to combine to form their own cluster. At step 2, the next 2 most similar are these over here. Step 3, these over here. So now you have, n-3 clusters, I think. And then you're going to keep merging. At some point, each pair will be its own cluster. So you can actually merge single data points into pairs to form bigger and bigger groups. But basically, it's like that. There's like that. I don't know. I feel like there are games and GIFs that you see around where you're like combining bubbles and blobs together. That's pretty much what HAC is doing. So at some point, you can actually keep going to the point where you end up with one gigantic cluster. And to go back from like to go back from 3 to 4 to 5 clusters, you just have to backtrack one step. And the thing about HAC, which is different from k-means, when you run k-means over and over again, you might get different clustering results. Maybe some fringe points get clustered differently. But for HAC, as long as your data set doesn't change, you're going to end up with the same dendrogram every single time. Any questions about how this works? Okay, so with HAC, other than the number of clusters that you have to define for scikit-learn's implementation of it, the hyperparameter that you tune is the type of linkage. And type of linkage is basically how you determine distance between groups of data points. So there are 3 main kinds of linkages. So first we have single linkage, where if you have 2 subclusters, for any 2 clusters, you just take one observation from each and determine their distance, do this over and over. And the single linkage is the overall minimum pairwise distance. So let's say we have these 2 clusters. The single linkage distance is this distance over here. So how you determine what to merge next will be by this distance. If I had one more cluster that was, let's say, over here, for example, with data points over here, 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 here. If I had this cluster over here, the single linkage for that will be, let me grab the arrow tool, and I think it would be this one over here. So for different groups, you can actually use different data points to compute the distances between different groups. So between this and this group, it would be this data point and this data point, but between this and this group, it's this and this data point. So this is single linkage. Next, we have complete linkage, which is pretty much the opposite of that, where the distance is actually computed by the furthest distance within each cluster. So over here, you can see that the distance is this one over here. This is actually really interesting if you have outliers. So if you have a lot of outliers, and let's say this cluster was a little bit bigger, and we had one outlier over here, that distance ends up being much, much longer than this distance that is shown over here. It also depends on what had happened to form this cluster to begin with, but complete linkage, basically you're using relatively longer distances across the board. And you do end up with different clustering results based on which kind of linkage you use. And then finally, you have average linkage, which, as the name suggests, you're going to compute the distance between every point in one cluster and every other point in another cluster and take the average distance. So here, this is just a mathematical formula for averaging all of these distances out. The distance that you use, I believe you can tune that as well, but that has a little bit less of an effect because the distances are all pretty relative to each other. But you could, if you wanted to, use Euclidean distance, L1, L2 distances, Manhattan, cosine similarity as well, so on and so forth. But this is probably the main hyperparameter that you'll see the biggest change in your clustering results for HAC. Questions at this point? Cool. Next, let's take a look at a dendrogram. So dendrograms are like this. It's basically a tree-like diagram. And if we could zoom in, I probably should have done like a truncated version of this, but every point at the bottom is a singular data point. And if we could zoom in here, and I know this actually takes very long to run, so I won't rerun it. You'll actually see that at every level, going from down here up here, you'll see where these linkages are occurring. So let's just say that if I wanted to have 2 clusters, I know that my 2 clusters are going to be whatever is connected to here and whatever is connected to here. If I want 3 clusters, it looks like it'll be this over here, and then I think 2 over here. I think this line's a little thicker than the other. But pretty much you just cut off your dendrogram at however many clusters you want, and those will be your clusters. So you can trim and truncate the dendrogram. This is another example of a dendrogram where it's basically like, and actually this for this data set, the way that it did its clustering, I believe, is such that you have 2,997 data points here, 1 data point here, 1 data point here, 1 data point here, I think. Dendrograms, usually if you have very large data sets, not very helpful to look at, but if clustering was very, very important to your task, someone might actually look at that. Cool. More importantly, let's compare these clustering results. So here I have, oh shoot, okay, good. Doesn't take too long to run. So here I'm running my K-means clustering and I'm also doing my HAC. So same thing, I'm doing my fit predict on both of them. Fit predict basically fits and does the prediction. So that's how I have my labels over there. And I can compare my results. So with 3 clusters, I think both of them will end up pretty similar. So let's take a look at when you have 4 clusters. When you have 4 clusters, these are what the clustering results look like for the 2 different clustering algorithms. So for the most part, kind of similar. You expect these 3 main groups to form, but the way that it does its 4th cluster is really interesting. K-means clustering is much more dependent on you see a much smoother boundary or a much clearer boundary over here. So you can see because it is looking at distance metric between centroid and each data point, you can see that this is a straighter line. Whereas for HAC, because it's looking at smaller blobs similarity to each other, you can end up with a less smooth decision boundary for your cluster, which I think is a really interesting effect of the bottom up versus top down technique. So you do end up with different clustering results. Which one you choose, maybe you use some scores, maybe you have, yeah, I would say use some scores unless you decide that one is better than the other, depending on your business case. All right, so to go more in depth with HAC, we talked about how the dendrogram and how that merging works. I think it's really interesting to look at how HAC works as you increase the number of clusters. So let me zoom out a little bit because you don't really need to read anything here. But with 4 clusters, it looked like this. When you have 5 clusters, this remains the same, and this actually splits up. So if we actually look backwards, we start with 8 clusters, 3 here, 3 here, 2 over here. When you decrease the number of clusters 1 by 1, you'll start to see subclusters merge. So going from 8 to 7, it seems like this light blue one and this gray one were the ones that merged. To go from 7 to 6, it is the pink and blue one over here that merged to form this. And then going from 6 to 5, it was these 2 that had an overall smaller distance, I believe. What did I use here? Whatever the default was, let's take a look. I think it was ward linkages. I forget what ward. Oh, minimizes the variance of clusters being merged. Okay. So yeah, HAC, this graphic is really just to show that when you are increasing or decreasing the number of clusters, you're really just taking the smaller clusters and putting them together, or taking your bigger clusters and splitting them apart. All right, and like I mentioned before, the metrics that you use to evaluate your clusters, exactly the same, not dependent on the algorithm that you use. So we're looking at silhouette coefficient over here. It also says that the best number of clusters is 3. So in summary, we talked about centroid-based and connectivity-based clusters. So K-means is centroid-based and HAC is connectivity-based. K-means has an element of randomness while HAC does not. And in context, you want to examine the data points in each cluster in order to manually label them. So over here, of course, this is a contextless data set. But let's just say we did our clustering and we ended up with the 3 groups as shown over here. Usually what you have to do is do maybe some like intercluster EDA, like really quick EDA, so that you can characterize the data points within each cluster to however to suit your data set. Other applications of clustering, if the goal of your project is not to cluster, and yeah, for this phase 4 project, there is no clustering project, clustering can be a really, really good EDA tool to just garner like main groups of data. So for example, if you were looking at the telco, the Seriatel data set, for example, maybe you can, through clustering, figure out, okay, there seem to be certain groups of customers, maybe ones that use the international plan, ones that call customer service a lot, something like that. And yeah, another way that you can do it, if you have unlabeled data and you want to just perform classification on something, clustering is actually a really neat way to get labels for your data. Of course, you will do this with a grain of salt, but if you just needed to implement classification, or yeah, if you needed to implement classification, that's one way that you can do it. The last thing I wanted to show you all is that k-means has predict probabilities, I think. Let me see, is it here? Cluster weights. There's somewhere where you can get the cluster probabilities, which let me find the transform. Okay, I can't find it right now, but I think that there's one way that you can do that. If not, then I might be mistaking something, but that's not super important for now. We'll talk about soft clustering later in the phase. There's actually a very, very commonly used soft clustering algorithm for text data. So when we get to NLP, I'm definitely going to talk about that. But yes, that is clustering. Main things to know is we talked about two algorithms, one that is top down, one that is bottom up. And to evaluate your clusters, it is very, very subjective, but also you have the elbow method and you have silhouette scores if it is not very subjective. Cool. Any questions? That's clustering. All right. Well, there's nothing else. Next week is going to be cool. We're going to talk about big data. That is going to be a very, very high level, study group. The labs for big data, just in case anyone is going to start looking at it. The labs for big data have you install Docker to work with this thing called PySpark. PySpark is basically like Jupyter Notebook, but for big data. Actually, let me go to there to just show you all. Yeah, they're actually going to have you configure some stuff. One downside is Docker recently went through a big change, and I think most recently a lot of people are having issues with downloading Docker and getting their stuff to work. So if it doesn't work, just know that is not the most important thing for right now, but it should work within Illumidesk. And then the other thing we're going to talk about next week is recommendation systems. Those of you who came to the talk that I did, what was it, last month? Pretty much the same thing as what I talked about then, but in a little bit more detail. So yeah, next week's going to be a fun one. Following week will be all time series. Great. Any final questions? Going once, going twice. All right, as usual, anything else you need, feel free to Slack me and let me know. This week, definitely you can take it easy. These topics that I talked about today and yesterday are not imperative parts of your project. So definitely to prevent burnout, feel free to take it easy. And yeah, reach out to me if you need anything at all. Don't forget to schedule your phase 4 reviews. I see some of you here who haven't scheduled it. And yeah, with that, I hope you all have a good rest of your week. I will talk to you all next week. All right.
Have a good one.
Bye, everybody.
Thank you. Have a good night.
Have a great night, guys. Thank you.